you turn on this again, right? So now you have two turn on at the same time. This turn on, turn on, right? So this thing in the circle, turning on, multiply the gain of the transistor at one time is completely turned on, induce large amount of current. This is what the latch-up works. What guys? In reality, it will not turn on. It will only turn on when the supply go high. Let's say put a 9 volt, then the diode will start to be current. Okay? Diode will start to be current, must multiply by this resistor. If this resistor is very small, it cannot never exceed 0.7 volt. If this resistor is very high, it exceeds 0.7, going to turn on NPN. When NPN turn, the drop voltage will drop here, turn on this device. And then it's going in the loop, activate at the time, you only have a large gain, current will start to conduct both parts. That's where the R, the overall R from supply to ground becomes smaller, huge current will flow. This is the phenomenon of SCF. Play, huh? You should be able to explain because you only understand what is forming PNP, MOS, what is forming NPN, MOS, right? Then you place it in this order. You place it in this order, then always remember when VDD go high, that's the way you start to have leakage. When leakage is there, multiplied by subtle resistance is when you first turn on NMOS, BJT. After NMOS turn on, then you will have a drop on the R angle. Then the PNP to turn on, then both turn on, you see a huge current. It's going to latching up mode. Boleh ya? Omega, huh? So you need to understand this, huh? Ganesh, okay. Faham? Yang tak dapat faham can ask me later personally, right? Can I go to the next slide? If you already understand this. Because if only one loop is on, you cannot conduct. It must both branch must on. When both branch on, then only you go into the loop circle. It amplify until at one stage is full turn on ready. Then huge current flow. That's it. Latch up never recover. So it always latching up ready. Okay, paham? Eman, boleh? Okay. So this, if you can able to explain, most of the time when the layout guys come to my company, I'll ask question. Can you explain me latch up how it works? Many people will not be able to explain. Even a 5 years experience from MNC will not able to explain. Because why? They only follow blindly from the designer, draw such a. How the designer bagi, akan just draw. But they don't really want to understand why designer asked me to draw this piece. Right? So I want to make improvement on you. When designer gives you schematic, understand before you start to draw. Guys, this will make you a good layout engineer. And over the time, you also can switch your field from becoming a layouter to go back to design if you are passionate. Okay. Boleh ikan lah? Ganesh? Right, terus. So I want to this because the first graph is putting up, but this is just to show you latch up can happen in two ways. One is when you inject current to the I/O pad. The current injector can be negative current or positive current. Also can induce latch up, right? The other thing is, what is this? This is what I say supply voltage, right? Supply voltage go high, then you can actually induce the latch up. That's it. Either supply voltage go high from 5 volt or you induce the current into your input or output pad. That's it. Itu yang menyebabkan latch up. So remember, how latch up can trigger when someone make the VDD go above the operation voltage, or during when you have like a digital circuitry, inject the current to the analog input output, you also will have a latch up trigger. Latch up means you only turn on the branch, right? Then it will terbakar the metal lamp and the circuit will not function. Yeah, so you are kind of thermal heat at the location. So the heat will flow to other devices. It's going to have a malfunction. Okay, guys. As I said, so what are the causes of voltage at VDD, current injected at the IO pad. These are the two main culprits. You must get very aware of these two culprits: transient voltage and also the injection current. Also the subtract noise coupling from the noisy block to the analog can cause match up. Improper power up and down. Let's say you are turning on off, right? When you turning on off, suddenly you see a spike at the supply. That also a chance for match up to happen, right? And then that's why. So what you need to do to avoid number 4 here, improper power up down sequence. What do you do?
Improper power up.
So what do you do? I told you, right?
Properly.
You power up, suddenly you see a spike at VDD. So what you can do to minimize spike? Add capacitor, right? Yes. When you add capacitor, the spike will get suppressed, right? So that's one way you can do it. And then high temperature operation, right? So as you know, when the temperature goes up, some of the mobility of electron in the NMOS or the mobility of the holes in the PMOS will also get excited. This also can cause a charge at the substrate itself. Okay? So remember this, capture this. One moment. Okay, so as usual, what are the technique we do for lecture? You see, guard rings never run away. Be it for electromigration, be it for ESD, or be it for even for the lecture, right? Antenna, yes, we don't do guard ring, right? Mainly guard ring will be helping us in our layout. So once you already expert that guard ring implementation, you already have become a seafood in your layout as well. Seafood. Right, so guard rings, and then you want to avoid the match-up adequate guard. Let's say you have too many guards, you have too many guards side by side, you want to keep a gap there. Because well to well also will have induce a match-up there. That means the electron can throw to other junction quite often, right? So you want to keep a distance as well because of different quality you have. So guard rings, well spacing, multiple substrate. This is what I keep on telling you. You draw the N-well, you draw the P-well, add so many wires, add so many contacts so that your R sub, your R and well can get reduced. So the base voltage can never go 0.7, this one can never come to 4.2 volt. Understand? So this is where the multiple substrate. Okay. Yeah. Remember, so deep and well also you can want to use for the lecture mitigation, right? So and then the proper pad ring design. So you want to avoid lecture due to high junction. So you want to select the right pad which can able to suppress the spikes at the voltage supply. So this is what you can do. Okay. Right. So farmer, what is lecture? Many of you were asking in the beginning what is lecture. So I already explained. First, when people ask what is lecture is a phenomena where huge current flow from supply to ground because a low impedance already formed. A low impedance already formed, current flow from VDD to ground. Most of the time, lecture cannot be recovered. That is, today someone power up, right? Suddenly you see the spike, lecture already happened. You see 50 milliamps, 100 milliamps current. So you turn off. Tomorrow you come to that, you power up again, lecture will be still there. Then the system is gone. You cannot use anymore. Right? Remember, because that's what is lecture. Second is, lecture is only can happen when you have PMOS and NMOS. Right? There is parasitic PNP and parasitic NPN need to be there. Then only the lecture can happen. These are the two things you want to understand and explain to the people who is going to interview you for the next job. Okay. That is clear. I see very confident. You're very confident. Okay. So now
Dia fine lah, tapi
Dia bukan jadi poli.
tak payah lah. Tapi it's okay kalau you want to check the thing, you can fine. Because you want to check the line cannot be so long also. But here, I think should be used more than right? It's same also, right? Yeah, understand. Sauce, brown. So go to the sister, right? Okay. Mana you punya V1 positive, V negative without label. Yes. So what you can do? Tarik balik guna metal. Tarik balik guna metal. Label and V plus V minus. Buat cross kan? Tak. Just tarik sampai sini lah. Saya lepas tu letak kontak. Ya, gate dengan metal dengan kontak kan? Okay. Apa dia? V plus ke V minus? Okay. Satu lagi. Jangan connect, jangan sampai ke sini lah. This small area pump. Tapi sini okey sebab ini yang metal dua kan? Boleh tarik metal dua. Tak masalah. Tarik saja. Okey. Letak metal. Right? Okey lah. But as long as you metal pun you cuba letak metal sini sampai sini. Sudah tarik metal sini. So you can get sampai sini. Sampai sini. Kurang tak boleh. Who else? Okay, so while waiting the rest to complete, so let's do the wrap up. Alright, so for today's class, we started with electrostatic. Today's class is what all about today's class? Reliability, right? Why reliability is important? Yes. Make sure it lasts long, so we have a long lifespan of the device, right? And under how we want to make sure that the device will last long? How we want to make sure that the device will last long? We use the lecture. Yeah, one of it. So that means we want to stress that under all the extreme conditions, right? Yeah. You want to apply different power supply, but still you need to follow the data sheet power supply. You cannot be extreme that more than that, right? So you want to stress them using different types of temperature, supply, right? And then current also want to use that, right? Yeah. So that's what we do on the EST things. And also, we also learned today what is the type of EST protection we want to use, right? So there be two basic EST type protection that you think will be helpful for you. Diode bias. There we have a diode from input to supply, and then the diode from input to ground, right? And in normal condition, what is the state of the biasing? The diodes. Reverse bias. In the normal condition, the diode clamp base is reverse bias, right? But they do have some leakage. But that leakage is not harmful or it's not bothered by the customer. That is okay to go, right? Some of the leakage even will be higher in the higher technology nodes, like 7 nanometer. Sorry, modern technology node, 7 nanometer or something, right? And then similarly, like if you want to use GTMOS, GTMOS also will have its own good thing. But at the end, either you use diode based clamp or GTMOS clamp, you want to what? Yes, you want to divert the current from the input to ground, right? Because if you don't divert the current from input to ground, what will happen?
Internal circuits.
Yes, it's going to damage the internal circuit. How is going to damage the internal circuit? Breakdown, right? The current, right? The huge current will go, and and then it build the charge at the gate. So when it build the charge at the gate, the voltage of the gate will grow. From 5 volt it will grow 6 volt, 7 volt, then it will break the gate. So this is how the ESD things looks like. So what are the ways you can enable the layout for the ESD protection? What are the steps? What do you do for to enable this ESD protection?
Input and out.
Sorry?
Just tests.
Right. Protection, right? So this is the so what you do is like this one I told you, right? So this is how you want to improvise. So first, when you apply this diode protection, you want to keep the diode protection closer to the IO pad, right? So that's rule number 1. So and then number 2 is you must draw the wire connection to the pad to sustain this much of ESD current, right? If you are designing a device for customer to sustain 2 kV, let's say 2 kV ESD, 2 kV will equal around 1 ampere. Then you must draw the input, output or VDD to sustain this much of current. What happens if I draw the current, a bit which is less than what it's supposed to be? So do now the method, right? In my real life, I've seen a number of cases of this because the layouter didn't really pay a full attention when the designer asked to fulfill. Of course, the layout have to review back with the designer. Somehow, the designer also have overlooked this. At the end, it went to fabrication, it went to the ESD test, it failed in the lab. And then when we take up the chip with microscope, then we found there's a big hotspot. When I say hotspot means where the current go and settle there. Current just but the tapung there only. So we saw a big hotspot. That's where the metal actually burn out. Metal open really because it didn't have enough current density to go through, right? So the other thing is you can add in guard rings, because guard rings you can collect the charges. So you see it's an ESD strike there. So you want to make more bad thing to the input, right? So before the ESD strike, you want to collect the charges and the thing you want to chunk away also to ground, so whichever the low impedance part you have, right? So that's what we want to understand about the ESD things, right? Okay. So the other thing is I also want to share how this ESD test is done in the lab, right? You already designed the chip, sand fabrication, right? So how they do? So once the chip is fabricated, of course it will go to the wafer test, right? After the wafer test, it's going to be packaged, different type of package. After it's packaged, then they are going to apply this model. How many models we know for the ESD? 3 models, right? What are those 3 models? Human body model, then machine model, some more charge device model. So among these 3 models, which is the most realistic, we are supposed to scan off CDM, right? Why that is more severe model? Yes, the current that we are going to apply is a very short duration, less than 1 nanosecond. The HPM model or the machine model, they can go like more than 10 nanoseconds numbers, but the CDM model is very short time. So when you apply something very short, it's very hard for you to control. You don't design a circuit and enter such a fast function. That's why it's going to be very like severe things can happen to your circuit, right? Okay, come back to the lab. How they check this ESD? Let's say the customer is asking, can you design the ESD to support up to 2 kV, right? 2 kilowatt. Then how they do is, first they were using something like a gun to apply a large voltage at the input, and then they will start from 500 volt. They will check 500 volt, right? But before they apply the ESD test, Right. So before they apply the EST test, first they will do some basic measurement. They say I design an amplifier. My amplifier has some leakage, this much of leakage to the offset. Right. They say in the offset I have a leakage only about 0.5 microampere. Right. Now they are going to apply a EST on the device, 500 volt. After they apply, they have to measure again. Check whether the EST is still 0.5 ampere or not. If before and after measurement 0.5 means the device is not damaged yet, right? And then from 500 volt, I'm going to go for the 1000 volt. They will have to apply the stress on the input or the input combination. Then they measure again and test the leakage. If the leakage still at 1 volt, 1 kV is still 0.5, that means the device is still passing. They say they apply one by one, right? Up to 3 kV, they apply the test. Now they measure the leakage. Leakage shoot up from 0.5 to 100 microampere. Now they know this is my limit. So my device has failed. So this is how they do the testing in the lab. So they will start from the lowest 500 volt up to step by step. 500 volt, 1.5 kilovolt up to 2 kV as it is. And then they have to do the comparison. Pre-test and post-test. Post-test is every time you stress, you have to refer back to the pre-test, right? So this is what they do for the ESC things, okay? And then the reason why if you have this charged device model, human body model, and all the machine model, because in the simulation we cannot really simulate them. Why we cannot simulate them? Because this ESC is not something fixed. It can happen at any timing, right? That's why the foundry will have very difficulty to simulate them. So that's why before we go to the foundry for fabrication, we have to use all the knowledge we have how to make the device to be operable with the ESC strike will happen. So then only we go to the fabrication, we can know whether it is really passing or failing. Right? So this is what we do for the ESC. Okay. Now the second thing is what? Electromigration. So electromigration, as you all know, is caused by the movement of atom on the metal because of the huge current flow out, right? So over the time, the atom or the electron being swept away from its original location, then it creates a hole, right? When you create a hole, it can create a large resistivity there, right? And it can also cause open or short on the metal, right? Whenever there is open, we know because of the large resistor, then will have the delay, parasites to the signal, right? That's what it can have. So one of the ways we can do to mitigate EM, we want to draw the metal bit larger, right? We want to draw the metal bit larger, and then another thing is we have to limit our current to flow on the metal. If you only draw 10 milliamps, you need to specify to the customer, don't let the current flow more than that. This is what to check. And of course, these are the two things you want to check, because the operation wise, how long the customer going to on the device is not on our hand, but we will give them the recommendation. You can this device only can go up to 10 years and so on, but you need to limit the current go through the metal and so on, right? Okay. Okay. We also know that in the modern technology, we can able to verify the EM, right? So they all do the things, and then the simulator, the schematic designer take the schematic expected, bring done. They will apply 1 ampere current on the test bench schematic, and then after they apply, they can have the tool able to check whether they can see any hotspot by the virtual simulation or not. So if the tool flag this area can have a hotspot, then they have to correct back to the layout, make the metal even wider and so on. So that's what we understood about EM, right? Okay. So you need to just understand what the ways you want to minimize the EM, right? Okay. So to mitigate the EM, we told, right, you need to use a larger metal. You want to use a lot of bias connection. You want to go for parallel connection of the metal to divert the current, right? So that the current will be equally split according to the metal capacity, right? Okay. So antenna effect, So what is antenna effect? It's just a quick word. You collect the long metal, collect the charge travel to gate, and then it explode the gate. Why the gate explode? Because cannot sustain that much of huge collection, charge collection, right? So what we do to mitigate the antenna effect? Jump metal. When you jump the metal, the charge it need to travel even long, right? It need to travel long and it lose its capacity there. As once the moment reaches the destination, it already becomes weak. So cannot really go and break the thing. The other thing is what they do. Antenna. You add the parasitic diode from the gate to lower potential source or anything, right? And this diode in the normal way is in reverse bias. It will not contact anything. What happens if you forgot to add diode? What will be next? The designer or the layout people forgot to add diode. Do you need to worry or not?
No.
Why? Yes, the foundry will help you to this. But always you need to double check whether the foundry already added the diode or not. Something. So this one we do the tapered process verification. Will happen all the time, right? So that two method how to mitigate antenna is able to understand and able to explain to people whoever asking you to do that phenomena, right? Right, latch up. So what is latch up? What is latch up phenomena?
Huge current flows for
The first word come from your mouth is huge current flow from VDD to ground. Because the resistance become VDD and ground become shorter, smaller. That's why huge current from VDD to ground, right? So the latch up happen in CMOS because you have these two parasitics. PNP coming from NPL coming from MOS, right? So this PNP and NPN combination, if you trigger that above the operating level, they will start to conduct, right? But how we want to minimize this latch-up thing from happening? Sorry?
Include more substrate.
Yes, the substrate connection, right? You know, right? We have R substrate, we have an angular substrate, right? So to make the thing, even you have a leakage because of the voltage go high, transient voltage or current being injected at the input output node, you must first make sure to reduce the substrate resistance as small as you can. How you want to reduce the substrate resistance as small as you can? How? You put a lot of taps across the guide. You put a lot of taps, then the resistance will become smaller and smaller and easy to shunt the current to ground or the current to VDD. Right? So this is what you should understand when you come to the latch up. So latch up will trigger if I just use NMOS. Well, latch up trigger if I just use NMOS.
No.
Or if I just use PMOS.
No.
So I need to have both combination to be there. Right? Okay. So now go back to this. So, right. So as you understand, right? So in the normal, once we are in this cross connection, in the cross section mode, right? This latch-up will be there. I mean the topology will be there, but it is not activated, right? So only it is activated when VDD go high beyond 0.7 then the supply, then you start to have leakage. When the leakage is there, the R sub it must be big enough to make this point go 0.7, right? So if this is small enough, the current leakage also is not strong enough to lift up this base voltage. Then you don't need to worry. And that's why you must put the base substrate resistance as small as possible, right? So this must turn on, this must turn on. Then only the loop will be created, right? When the two loop is created, then keep on latching from 10 microampere leakage is going to be 100-200 milliamps of leakage because of the internal loop amplification. Right? Amplify, 10 micro go up to 100, 200, finally it's going to blow up all the metals wherever the circuit is connected. Understand? So that's what the latch-up phenomena is. Okay? So latch-up can be two ways to happen. How is that? either the supply voltage go beyond the 5 volt or whichever, right? The transient supply voltage, right? Or current is injected at the input node, IO node. Remember, latch up can happen because of two reasons. Either the supply voltage go high above what is allowed by the designer, or you start to inject huge current coming from the switching of the digital circuit, whatever, into the IO. That's it. You need to remember, right? Okay. So this one is showing the transfer voltage there. Right, so remember, ESD or transfer voltage right, or the current injection in the IO input. These are two main reasons. The other two is for you to just understand. And you should know one of the techniques you need to apply to make the lecture more robust. So you need to use couplings wherever is possible. You want to make the well-to-well isolation to have a distance. Otherwise, that's going to trigger the lecture because the distance for the resistance becomes smaller, right? So you need to reduce that. You want to use a multiple substrate and put a lot of well type connection. This is what it's supposed to do. Let's just follow that. So deep and well. If you have the option in your process deep and well, just utilize deep and well because you already pay that with the package. Just use. But some foundry they ask you to pay extra for this mask. So you need to use wisely. If this mask is going to be very costly, then the management will not allow. But you can challenge also. You want performance or you want to spend money, you have to challenge them how you want to work. Okay? Right. Okay. Right. Okay guys, right? So this is we already do the what you call the exercises to make you understand what you call before the first video dispatch yesterday and today we do the isolation. So for exercise for today, we will do tomorrow on the group discussion, right? So for the summary for today, we wanted to cover what is ESD, we wanted to cover what is latch-up, we wanted to cover what is antenna, and also we want to cover yes, micro-migration, right? So we already see what is causing what and what are the basic techniques we want to apply to cover all these four big brothers to affect our reliability. As a designer, we must be very sure we want to keep their influence as small as possible so that we can have very healthy chip coming back from the silicon fabrication. Right? Okay, so this conclude for the class for today. Right? Any questions you want to ask before we end up our session today? Right? Okay, good. That's what I want to tell you guys. Understand. Right? So I will test your understand tomorrow. Right? So be prepared. Ulang kaji, mari ulang kaji. Tomorrow on 4th day, you will be doing some more other things. Right? This one to make sure that what I am teaching, you guys absorb, and that's my role in here. Right? I want to break the barrier. Academic, industry, we are in the center. When you go to industry, people become more popular of you, you can just catch up. Okay, thanks.